Alrighty, howdy folks. Today we'll look at the Laplace transform. So we have moved from chapter 4 to chapter 7, and after chapter 7 all we need to cover is one section in chapter 6 and on Cauchy-Euler equation, and when we do that we are done for the semester. And Cauchy-Euler equation is very, very simple. So without much further ado, Chapter 7, Section 7.1 is about Laplace transform. Alright, so like any mathematician would do, I'll give the definition of a Laplace transform. Let f be a function defined for t greater than or equal to 0. This requirement is actually not necessary, but usually, when we talk about Laplace transforms, we talk about real world scenario where we have some finite time and we could always pick some particular time as being 0 and measure everything from that time, right? And so that's why this stipulation, but some people don't put this condition, okay? Then the Laplace transform of f is simply a certain integral. We write this curly L of f of t to indicate Laplace of f of t, lowercase f of t. Why am I saying lowercase f? Yeah, because after you take the Laplace, what you get is some function of s. Take a look at this. Is equal to integral 0 to infinity e to the negative st f of t dt. So if you notice, when you evaluate this integral, that s is in fact a variable, but in this case, because we are integrating with respect to t, we can treat that s as a constant and integrate. So you work it as if this is e to the negative at f of t dt, a being a constant. Just like that, you work this one out, okay? But once you plug in the limits for t, the 0 to infinity in this case, what results is a function of s. And that function of s, which is the Laplace of f of t, is what is represented with an uppercase f of s. Okay, that's why we need to clearly distinguish between the lowercase f and uppercase f. You sort of make a mental image of this. Lowercase f means a function of variable t. Uppercase f is the Laplace of it, is a function of the variable s. Okay? Cool. That's it. This is the definition. You get a Laplace of f of t to be 0 to infinity e to the negative st f of t dt. Now, one question that might pop up in your head is, why? Who cares? Why are we doing this transform? The thing is, oftentimes engineers and mathematicians and physicists resort to transforming things to a different system. For example, when we go from Cartesian coordinate system xy to a polar coordinate system or theta, that's a transform. Okay, they were transforming the coordinates from Cartesian to polar. Why do we do that? Because there are certain advantages to doing that. In some instances, looking at a problem in terms of polar coordinates makes the whole problem very, very simple. And all the chemical engineers and mechanical engineers and even civil engineers, when you do fluid mechanics, you will notice the advantage of solving things in polar and cylindrical coordinates. The idea there being, suppose something has circular symmetry. What does that mean, circular symmetry? Think of a pipe, a regular cylindrical pipe. Now, as water or fluid is flowing through that pipe, if you can write the equations in terms of polar coordinates or cylindrical coordinates, the equation becomes very simple. Maybe I can pick a simpler example than that. if I have a circle with the center at the origin and radius is r, what's the equation of this circle? Would you agree is x square plus y square is equal to r square? Right? Simple equation. And do you know what this equation is in polar coordinates? The same circle with the same origin as center and radius r. The equation of this circle in terms of polar coordinates is very, very complicated. It is as complicated as lowercase r is equal to uppercase r. Yep. As simple as that. What does it mean? What that means is, in polar coordinates, we have r and theta as the variables, right? So what this is saying is, no matter what the theta is, r is going to be uppercase r. The radius is going to be uppercase r. Okay, so theta equals 0 radian or 0 degrees. What is r? R. 1 degree, r. 2 degrees, 5, So it's just a circle. Notice how simple this equation is the moment we use polar coordinates as opposed to Cartesian coordinates, right? In the same way, when we take a function of t and transform it into this s using a Laplace transform, certain problems become very, very simple. You talk to anybody, your electrical engineering friends or mechanical friends or chemical friends who's taking control systems. They will tell you, circuits too, for example, and also my daughter is taking control systems in chemical engineering, right? All those people will tell you how ridiculously important Laplace transforms is for them, because everything becomes simple the moment you transform a function of t into a function of s using Laplace. Okay, so that's one of the advantages of Laplace. But obviously, if I'm touting the greatness of Laplace so far as control systems is concerned, what in the world is it doing in differential equations? We will show that in fact, even differential equations can be solved using Laplace transforms. Okay? And so, for the most part, what's going to happen is, think of the sections 7.1, 2, 3, and 4. We never even touch a differential equation. Only when we get to 7.5, where we talk about applications of Laplace transform, that's when we will pick differential equations and solve them using this method. Okay, so for hang on tight for 4 sections where you won't even probably hear the word differential equation, even though this is a differential equations class. Okay, all right. So having given you the definition, could I ask you a problem like this? Hey, what's Laplace of 1? Can you figure out just based on the definition yourself as to what do you need to do? I told you Laplace of f of t is equal to integral 0 to infinity e to the negative st f of t dt, right? Now, when I ask you Laplace of 1, immediately what should you think? Oh, you mean f of t is equal to 1. Yeah, I'm saying f of t is 1. So what should the Laplace of f of t be? Plug f of t into the integral. Right? Is that what you thought? If you did, that's exactly the idea. So solution is Laplace of 1 is wherever you see f of t, you just plug in 1. Right? Okay, now the question is, do we know how to integrate e to the negative st dt? I told you a while ago, look at s as a constant, that's it. So e to the negative at dt would be, the integral would be e to the negative at over negative a, right? So same idea, e to the negative st over negative s evaluated from 0 to infinity. Cool? All right, now I need to point out something. So when we have a definite integral, what is it that we are supposed to do? We are now supposed to plug in the upper limit and take that, whatever you get, minus what we get when we plug the lower limit, right? Upper limit stuff minus the lower limit stuff. Okay, so plug, I said, the upper limit. If you say plug infinity, mathematicians will have a heart attack. Did you say to plug infinity? You cannot plug infinity, man. What are you, stupid or what? Okay, chill. So, what we will do is, while we understand, basically it sort of boils down to plugging, but don't say plug infinity, okay? Instead, if we say figure out the limit as t approaches infinity of this quantity, right? We are supposed to plug infinity for t, don't say that. Instead say find limit as t approaches infinity of whatever this stuff, e to the negative st over negative s. Now a mathematician is happy. Cool? And for 0, you can say plug 0 for the lower limit 0. You can say that. So I'll be careful and say negative 1 over s, limit as t approaches infinity of e to the negative st minus e to the c. Notice, because we are plugging in for t, that negative 1 over s is a constant multiple which can be yanked outside. Are we cool? Okay, now the question boils down to, what in the world is limit as t approaches infinity of e to the negative st? Okay. As t goes to infinity, can we say st gets bigger and bigger? So e to the negative st gets smaller and smaller, approaches 0? Can I say that? If you readily agreed, you are partially correct, right? If you said, yeah, man, like for example, e to the negative 2t, what happens to that as t goes to infinity? Yeah, that goes to 0. Negative e to the negative 3t, yep, that goes to 0. But then who said s has got to be a positive quantity? What if s were to be a negative quantity? Let's say s is negative 3. Then wouldn't this become e to the negative of negative 3t, which is e to the positive 3t? In that case, wouldn't this go to infinity? So be careful, be slightly careful about something like that. And so you can always put this condition. Okay, I don't want this to go to infinity where we have to say the Laplace doesn't exist. If s happens to be negative, the Laplace doesn't exist because this limit goes to infinity. Fine, we are not interested in that case. We are interested in the case where it does go to 0 and gives us something finite. So we will stipulate the condition that s is strictly greater than 0, and therefore we say, okay, this is negative 1 over s, 0 minus 1 in the event s is greater than 0. We'll put that condition. Cool? So what did we find? Laplace of 1 is equal to 1 over s provided s is greater than 0. Simple? So you just figured out your first Laplace transform. Cool. Let's proceed. Find Laplace of t. How do you do this? Again, go to the definition. Laplace of t, here f of t is t, so plug t for f of t. Okay, so we have 0 to infinity e to the negative st times t dt. How do you integrate that? By parts. So trust me, this is what you get if you apply the integration by parts. Okay, test this out. So on a separate sheet of paper, pick up a sheet of paper and figure out integral t e to the negative st, thinking of s as a constant, and check whether or not you get this quantity. Cool? All right. So now, quote unquote, plug infinity for t, which means evaluate limit as t approaches infinity of that quantity for the upper limit, minus the lower limit. When you plug in 0 for t, clearly this is 0 times 1, which is 0 over negative s. That's why it is 0. And e to the negative 0 is e to the 0 is 1 over s square. That's what I wrote. But then let's focus on this guy now. What is negative 1 over s is a constant here, constant multiple here, so I can pull that out. So everything hinges on what this limit as t approaches infinity of t e to the negative st is. Would you agree? Limit as t approaches infinity of t e to the negative st. Any thoughts on that? Well, let's put the condition again that the s must be greater than 0. Tell me in that situation what happens to this. Okay. Would you agree? I can write this as t over e to the st, right? E to the negative st can be written as 1 over e to the st. So I can write this as t over e to the st. So as t goes to infinity, we have the top going to infinity and the bottom also going to infinity, because we already said s is greater than 0. So we have infinity over infinity. But a simple argument can be made. Which one goes to infinity faster, the t or the e to the st? Exponentials grow very fast. So we have to say the denominator e to the st goes to infinity faster than the numerator t. Therefore, we have a quantity being divided by a much larger quantity as a limit that goes to 0. Okay? So limit of t e to the negative st as t approaches infinity is 0 provided s is greater than 0. Done. And we already put the condition s is greater than 0, so e to the negative st limit of that would be 0 as well. So this whole thing just goes to 0, leaving us with 0 minus 0 minus the quantity 0 minus 1 over s square, which is 1 over s square. Like I said, provided s is greater than 0. Simple? That's the idea. Now, sine kt, this is a pain. Its idea would be the same, just that the integral is a little bit of a pain, and I'll just invoke the result. Okay, you did this in Cal 2 quite a bit, and so by using integration by parts, you say I is equal to integral e to the negative st sine kt dt, and you get another I kind of a thing back and all that blah blah blah. I'm not going to show you that. Okay, so now let's ask again, when we do limit as t approaches infinity of all of this, what are we going to get? We have e to the negative st times sine kt. Let's make the same argument as before. That is, write this as sine kt over e to the st. Let s be greater than 0. So we have a sine kt is a small number that oscillates between -1 and +1. But we are dividing that by a very large number, right? Excuse me. We are dividing that by a very large number, and so that limit is 0. Same argument goes with cosine kt over e to the st. That also goes to 0. In essence, this whole limit just goes to 0, leaving us with k over s square plus k square. So, ladies and gentlemen, what is Laplace of sine kt? K over s square plus k square, provided s is greater than 0. Cool? All right. So let's pick up some problems from the book. in exercise 7.1, problem 3 gives us a function which is defined in piecewise fashion. Okay, so the idea is still the same. We need to apply the definition, that is integral 0 to infinity e to the negative st f of t dt. Notice here I wrote this as uppercase f of s. So Laplace of lowercase f of t, a function of the variable t, is equal to the uppercase f of the function of the variable s. That's just this 0 to infinity. Now, what do we plug for f of t? Well, it depends on what t is, right? If t happens to be between 0 and 1, we will replace f of t with a t. On the other hand, if t is greater than or equal to 1, we'll replace that f of t with a 1. So what that means is, I'm sure you guessed this, we need to split this into two integrals, right? An integral going from 0 to 1 and another integral going from 1 to infinity. That's exactly what I have done. And in the interval 0 to 1, I replaced f of t with a t. And in the interval 1 to infinity, replaced f of t with a 1. And the rest is straightforward. Integration, plug, chug, and all that stuff. Cool? And I made all the arguments about what that limit ought to be and all that stuff. And so, take a look at this. All it does is, it gives us that the Laplace of this particular f of t is 1 over s square minus e to the negative s over s square. Cool? All right. So, Laplace transforms of some basic functions. Laplace of 1 is 1 over s. We already proved that. In general, Laplace of any t to the n is n factorial over s to the n plus 1. N has to be, what should n be? N has to be a natural number, a whole number rather. Would that work? Yep. N has to be a whole number here. Whole number meaning could be 0, 1, 2, 3, 4, 5, 6, so on. Okay, because n cannot be just any real number. T to the 0.3, let's say. Well, that's 0.3 factorial. What 0.3 factorial? At least in your level, we have to say 0.3 factorial, we don't know what it is. But when you get to slightly higher level, you will learn about something called a gamma function, and you can actually talk about factorials of fractions and stuff like that. So right now, because we are not familiar with gamma functions and all that, let's restrict ourselves to n being a whole number. Cool? So Laplace of t to the n is equal to n factorial over s to the n plus 1. And Laplace of e to the at, we can show that to be 1 over s minus a. And Laplace of sine kt, we derived this k over s square plus k square. Laplace of cosine kt is s over s square plus k square. The book talks about Laplace of cosh and sinh also. I won't do that. Okay, if you see any problem on cosh and sinh, ignore it. Don't worry about it. After all, cosh x is nothing but e to the x minus e to the negative x over 2. So you can always did I say cosh is no sinh x is equal to e to the x minus e to the negative x over 2, and cosh x is e to the x plus e to the negative x, the quantity over 2. So you can always change that cosh and sinh to e to the some power, okay, and be done with it. So I'm not going to worry about the cosh and sinh, the hyperbolic ones. I would expect you to memorize this, okay? You must memorize Laplace of 1, Laplace of t to the n, and all these 5 things. And further, there are basic properties of Laplace transforms. The first one is, Laplace of f of t plus or minus g of t. Any guesses as to what that ought to be? Laplace of a sum. Is the Laplace of a sum equal to sum of the Laplaces? If you take a wild guess, I'm sure you will say, yep, it is. But I'm asking you to take slightly lesser wild, but more of an educated guess. Can you think of what it ought to be? Laplace of f of t plus m. Should that be Laplace of sum should be equal to sum of Laplaces? The answer is, of course it has to be. Why? Because, after all, Laplace transform is nothing but a sort of integral. Right? Is the Laplace, is the integral of a sum equal to sum of the integrals? Yeah. So, Laplace of a sum or difference being equal to the sum or difference of the Laplaces makes perfect sense. Makes logical sense, right? So yes, if that's the thought process you applied, you are absolutely right. So we have Laplace of f of t plus or minus g of t. Okay, again, always think in terms of integrals as you try to answer this question. If I have a constant multiple, Laplace of a constant multiple c times f of t, can I yank that c outside? The way you think about it is, if I were to have an integral c times f of t dt, can I yank the c outside of the integral? Yeah. Okay. If that is the case, you can do the same thing with Laplace. Cool. Is Laplace of f of t times g of t equal to Laplace of f of t times Laplace of g of t? Big time not equal to. Because integral of a product is not equal to product of the integrals. The same thing applies here. Laplace of a product is big time not equal to Laplace of f of t times Laplace of g of t. Cool? Alright, so keep that in mind. Now, find the Laplace transform of f of t equals to t minus 1, the quantity cube. Here, what we are saying is, you don't have to apply the definition of Laplace. That is, you don't have to evaluate that integral 0 to infinity e to the negative st times this f of t. That would be a pain because you would end up with a t cube e to the negative st, and oh lordy, that would be a pain to evaluate. Now, does this remind you of something that you've done before? You remember back in Cal 1, initially you were taught the definition of a derivative as, the derivative f prime of x is equal to limit as h approaches 0 of f of x plus h minus f of x all over h, and so find the derivative of x square, f of x equals x square. And those who already had calculus 1 would look at it and go, easy, that's equal to 2x. And those who never had Cal 1, they're like, man, how'd you get that? I thought you were supposed to do the big long limit, man. And the teacher will say, yeah, but you're not using the definition. So you better use the definition and tell me what the derivative of x squared would be. And so you would have to painstakingly go through limit as h approaches 0 of x plus h the quantity square minus x squared divided by h, expand that out, then simplify it, plug the limit, blah, blah, and finally you get 2x. And the guy who already had the calculus 1 would be going, ha, told ya. Right? It's the same idea here. I could very well ask you to find the Laplace by using the definition. And I clearly tell you to use the definition, you must do the integral thing. Okay? But after you get practice with after you demonstrate sufficient understanding using the definition, you have the luxury of just using this formulas that we had, in the previous, this stuff, all these 5 ones. So right now we can use the Laplace of basic functions and figure this one out. The only nagging thing here is, do we know how to expand 2t minus 1 the quantity cube? Recall that a minus b the quantity cube is a cube minus 3a square b plus 3ab square minus b cube. In fact, I usually remember it as a cube minus 3ab times a minus b. 3ab times, a cube minus 3ab times a minus b minus b cube. I remember it that way. Anyway, so that when you expand that middle term out, this is what you get. So the moment you recall this problem is piece of cake. You apply that a minus b the quantity cube to this, and this expands out to 8t cubed minus 12t squared plus 6t minus 1. Now, is the Laplace of a sum or difference equal to difference or sum or difference of the Laplaces? Yep. So we can separate this out as Laplace of each one of these things, and a constant multiple can be yanked out. Laplace of t cube, that looks like t to the n, with n being equal to 3. We know Laplace of t to the n is n factorial over s to the n plus 1. That's precisely what I applied. N factorial is 3 factorial here, and s to the n plus 1 is s to the 3 plus 1, and 8 is that constant multiple. Similarly, t square, the Laplace is 2 factorial over s to the 2 plus 1, and so on. Right? That's it. 3 factorial happens to be 3 times 2 times 1, which is 6. 8 times 6 is 48. So that's why I wrote 48. All right. Let me tell you something here. 3 factorial, 4 factorial, 4 factorial would be just 4 times 3 times 2 times 1 is just 24. 5 times 4 times 3 times 2 times 1, which would be 5 times 24 is 120. Now, if God forbid, I gave you something like, hey, what's Laplace of t to the 20? And you say, aha, that's 20 factorial over s to the 20 plus 1. Do not go around figuring out exactly what 20 factorial is by hand. You are not impressing me if you do that. Okay? I don't want you to be spending time figuring out a large number like that and spending all your time on that. You leave that as 20 factorial. I'll give you full credit. Cool? All right. So, that's it. That's how you solve this problem. Let's see. Laplace of e to the 4t minus e to the 2t the quantity square. Now, would you agree we need to, what happened there? Let me fix that quickly. I thought so. Okay, sorry about the delay. I hope it didn't miss the recording part. Good, that's still going on. All right. Sorry about that. Here, Laplace of f of t equals f of s is Laplace of this guy. Would you agree that we need to expand this out? We have a minus b the quantity square, which is a square minus 2ab plus b square. So e to the 4t, the quantity square, right, is what? What is e to the 4t? That quantity squared. Do not say e to the 16t square. No, it's not. A to the m, the quantity raised to n is a to the m times n, right? So e to the 4t times 2 makes it e to the 8t. E raised to the quantity 4t times 2 is e to the 8t. Okay, cool. Minus 2 times e to the 4t times e to the negative 2t is a to the m times a to the n is a to the m plus n. So e to the 4t minus 2t is e to the 2t, and this guy will become e to the negative 4t. All right. Then we saw that Laplace of e to the at was 1 over s minus a. Right? You probably aren't familiar with yet. Those 5 things, you please be sure to remember them, memorize them. So Laplace of e to the at is 1 over s minus a. So this should be 1 over s minus 8, Laplace of this. E to the 2t, Laplace should be 1 over s minus 2. E to the negative 4t, Laplace should be 1 over s minus negative 4 or s plus 4. That's it. Cool? All right. Then, what's with this guy? Okay. Yep, there's a couple of problems which are kind of interesting in your book. Sine of a plus b, recall that that's equal to sine a cosine b plus cosine a sine b. Similarly, sine of a minus b is sine a cosine b minus cosine a sine b. So if we were to add, cosine of a minus b and cosine of a plus b are like this. If we were to add these two, then we notice that on the left hand side we would have sine of a plus b plus sine of a minus b. Oh, by the way, do not tell me that sine of a plus b is just sine a plus sine b. Big tam not equal to, okay? So sine of a plus b is big tam not equal to sine a plus sine b. Okay, so sine of a plus b plus and the cosine a sine b and this negative cosine a sine b add up to 0. And we end up with a sine a cosine b plus sine a cosine b, which is 2 sine a cosine b. And similarly on this side, when we add both these equations, sine a sine b is cancelled, and you get cosine a minus b plus cosine of a plus b to be 2 cosine a cosine b. Which means, what did I do here? Well, I'm saying that if we were to subtract the bottom from the top, right, cosine of a minus b minus cosine of a plus b is what you would have on the left hand side, but this time the cosine a cosine b is cancelled, and this becomes sine a sine b minus negative sine a sine b, which would be sine a sine b plus sine a sine b, which is 2 sine a sine b. Okay? Now, these 3 results are important because from them we can glean these particular nuggets of wisdom, which is sine a cosine b based on this is 1/2. I'm dividing both sides by 2. 1/2 of this stuff, sine of a plus b plus sine of a minus b. What is that? Sine a cosine b is 1/2 of sine of a plus b plus sine of a minus b. Similarly, cosine a cosine b is 1/2 of cosine of a minus b plus cosine of a plus b. And sine a sine b is 1/2 of cosine of a minus b minus cosine of a plus b. These 3 results are very important because something else I needed to cover. Okay. Another important result is that recall that cosine of 2 theta is cosine square theta minus sine square theta. That's one version of this formula. And the second version is we could replace cosine square theta with a 1 minus sine square theta, right? Let me repeat that. We could replace cosine square theta with 1 minus sine square theta. Or equally likely, we could replace sine square theta with 1 minus cosine square theta. In fact, we will do both. We'll replace cosine square theta with a 1 minus sine square theta, in which we get cosine 2 theta to be 1 minus 2 sine square theta. And we will replace sine square theta with a 1 minus cosine square theta, in which case we get this. Why are we doing all of this? Because we want to be able to figure out what sine square theta would be in terms of this cosine 2 theta and a constant. And so if we solve for sine square theta, then we get sine square theta to be 1/2 of 1 minus cosine 2 theta. Missing another parenthesis on there. Okay. 1/2 of 1 minus cosine 2 theta. Similarly, cosine square theta is 1/2 of 1 plus cosine 2 theta. All these 5 results are very important to remember. Sine A cosine B, cosine A cosine B, sine A sine B, sine square theta, and cosine square theta. Because when we are asked, find Laplace transform of cosine square t, the same thing applies even when you're doing integration. If I ask you, hey, what's integral of cosine square x dx? There is no simple way. And do not tell me, hey, integral of cosine x is sine x, man, so integral of cosine square x is sine square x. No, it's not. Big time no. Right? The same thing here. Okay, what's the big deal? I'll figure out Laplace of cosine t and multiply that by Laplace of cosine t. No, you cannot do that. Laplace of a product is not equal to product of Laplaces. So the only way, at least that I know of, to solve this one is to be able to use the identities that we just derived and say, okay, this cosine square t is nothing but 1/2 of 1 plus cosine 2t. Okay, so Laplace of 1/2 of 1 plus cosine 2t. Now, once you recognize that, piece of cake. There's nothing to it. Laplace of 1/2 is just a constant, so 1/2 times Laplace of 1, which is 1 over s, so 1/2 times 1 over s. Laplace of cosine kt is s over s square plus k square. So we already have that 1/2, so that's what I have here. See, the moment you use the identity, this Laplace of the, had it been an integral, they both would have become very simple. Okay? In the same way, if I have Laplace of cosine 8t, cosine 2t, there is no simple way. But if you recall that identity, that cosine A, cosine B is 1/2 of cosine of A minus B plus cosine of A plus B, then we are done. 1/2 of cosine of A minus B plus cosine of A plus B, A being 8t and B being 2t. Right? So this reduces to 1/2 of cosine 6t. So just like a while ago I said, Laplace of cosine kt is s over s square plus k square. So apply that and you're done. Cool? Alright, and you're responsible for 1 through 42. And the kind of problems that I'll ask you is, I will say, use the definition, and I'll bold that phrase, use the definition. If I say that, you must use the definition. But if I don't, I just say, find the Laplace transform of something, then you can use these formulas and the properties of Laplaces. Cool? Alright. And let me go ahead and how much time elapsed? Yeah, since it's 44 minutes only, I'll go ahead and record the other one, Laplace of inverse Laplace transform, section 7.2. should be somewhat easy. Here is the idea. Inverse Laplace transform, the definition is, if Laplace of f of t is uppercase f of s, then that implies Laplace inverse of f of s is just f of t. Okay, seems fairly obvious to me. Okay, so what do we know? We know Laplace of 1 to be 1 over s. So if I ask you, hey, what's Laplace inverse of 1 over s? Duh, it's just equal to 1. Yep. Then Laplace of t to the n is n factorial over s to the n plus 1. Right? What is Laplace inverse of n factorial over s to the n plus 1? Duh, that's equal to t to the n. Oh, lordy. Okay, sorry about that, folks. Laplace, okay, so Laplace inverse of n factorial over s to the n plus 1 equals t to the n. But the thing is, problems won't look like that. Nobody will tell you, hey, what is Laplace inverse of, and choose n just right. For example, 4 factorial over s to the 4 plus 1. Nobody will tell you that. Usually, it shows up as Laplace inverse of 1 over s to the 5. Or Laplace inverse of 500 over s to the 10. The top would be whatever we want, right? And so this is not a really useful version of it. However, the useful version, I would say, is Laplace inverse of 1 over s to the n is t to the n minus 1 over n minus 1 factorial. Cool. Laplace inverse of 1 over s to the n. This is the one that you need to memorize. Now, of course, this logically, this comes from this one, right? How? No, n factorial is just a constant. N is a constant, so n factorial is a constant. Okay. And what's a good way to explain? Okay, how about this? Go backwards. Take the Laplace of this guy on the right-hand side and tell me whether or not you would get 1 over s to the n. Clearly, 1 over n minus 1 factorial is a constant multiple times Laplace of t to the n minus 1. Laplace of t to the n minus 1 is n minus 1 factorial over s to the n minus 1 plus 1. Right? What did I do? I'm applying this concept. Laplace of t to the n is n factorial s to the n plus 1. But in this case, if we don't have a t to the n, instead we have a t to the n minus 1. So this would be n minus 1 factorial over s to the n minus 1 plus 1, which is nothing but s to the n. So we would have a n minus 1 factorial on the top and a n minus 1 factorial on the bottom, which divide into 1. And so we are left with 1 over s to the n. So, yep, this formula must be correct. Cool? If you got it, good. If you didn't, don't worry about it. Memorize this guy. Laplace inverse of 1 over s to the n is t to the n minus 1 over n minus 1 factorial. Alright, Laplace of e to the at is 1 over s minus a. So Laplace inverse of 1 over s minus a is, you guessed it, e to the at. Sine kt. Laplace is k over s square plus k square. Laplace inverse of k over s square plus k square should be sine kt. But I'll submit to you that nobody is going to make sure that you have a perfect nice k on the top. That k over there could be whatever they want. For example, we could have a problem like Laplace inverse of 5000 divided by s square plus 2 square. S square plus 4, in fact. Nobody will nicely write down that 4 as 2 square. So you will have some 500 over s square plus 2 square, s square plus 4. Well, you interpret that, oh, you mean k is 2 in this case. So the point is, what if this k is not there? And so a useful version, what? I didn't do a useful version? I'm so stupid. Okay, based on this, would you agree that if we wanted Laplace inverse of 1 over s square plus k square, all we need to do is multiply by a k and divide by a k. So basically, Laplace inverse of 1 over s square plus k square would be 1 over k sine kt. That's what I'm saying. Whereas Laplace of cosine kt is s over s square plus k square. This doesn't have any issues like that. And so that's just cosine kt. The order in which it shows up, I didn't have that order right. Oh, lordy. Sorry about that, folks. So I do have the useful version for this one. Okay, that's what I said. Laplace inverse of 1 over s square plus k square is 1 over k sine kt. Cool. So let's apply this to something like this. Now, for these inverse Laplace transform problems, you really need to be good with partial fraction decomposition. Oh man, I hate that. I know. There's no choice. You better be really good at partial fraction decomposition. Okay? Because to find the Laplace inverse, the moment you split this into partial fractions, piece of cake it is. All right. So that's going to be 2 over s minus 3 plus 3 over s plus 2. You remember that cover method that I talked about? Where, because these s minus 3 and s plus 2 are linear factors that are not repeating, linear, right? Because you have as plus b, a1s plus b1, a2s plus b2, that form, they are linear factors. In that case, we can use a quick cover method and be done with it. How does that cover method work? I got 2 here, but leave that as a blank. Blank over s minus 3 plus blank over s plus 2. What goes on s minus 3? To figure that out, you need to do 3 things. Okay? First thing is, set s minus 3 equal to 0 and solve for s. You get s equals 3. Cool? First step is what? Set the denominator equal to 0 and solve for s. You get s equals 3. Second step, cover up that s minus 3 on the left hand side. Cool. And now, third step, plug that value of s equals 3 that you got into the left hand side. You've already noticed, you already covered up that s minus 3. So when you plug 3 for s, you get 5 times 3 is 15, 15 minus 5 is 10. Over 3 plus 2 is 5. So 10 over 5 is 2. Ta-da! That's what I have here. Similarly, to figure out what goes on top of s plus 2, same 3 steps. What is the first step? Set s plus 2 equal to 0 and solve for s. You get negative 2. Come here and cover up the s plus 2. And plug, third step, plug negative 2 for s. 5 times negative 2 is negative 10. Negative 10 minus 5 is negative 15. Negative 2 minus negative 3 is negative 5. So negative 15 over negative 5 is positive 3. And lo and behold, that's exactly what I have here. Now, Is Laplace inverse of a sum equal to sum of the Laplace inverses? Yep, think of it as like the inverse of an integral is the derivative. Is the derivative of a sum equal to sum of the derivatives? Yes, it is. So you can split this out, and 1 over s minus 3 is the Laplace inverse of that is e to the 3t, and so 2e to the 3t. S plus 2, 1 over s plus 2 is e to the negative 2t, so 3e to the negative 2t. Done. Okay. In this case, we are better off just expanding this out, foiling this out. So we get 4 over s square minus 4 over s to the 4 plus 1 over. And remember, 1 over s to the n, Laplace inverse of 1 over s to the n is t to the n minus 1 over n minus 1 factorial, or t to the 2 minus 1 over 2 minus 1 factorial, that is t to the 1 over 1 factorial, or just t, 4t. And for this, 3 factorial 4 times, 3 factorial over t cube over 3 factorial, and t to the 5 over 5 factorial as Laplace inverse of 1 over s to the 6. That's it. Okay. I multiplied this 5 factorial and said 120, but if you left it as 5 factorial, I'll give you full credit. Oh, okay. Got it. Oh, dang. For a second, I was like, did I say 3 factorial is 3? Nope. But in fact, this is 4 times t cube over 6, which reduces to 2/3. Okay. All right. Next one. Partial fraction decomposition. You remember this one? This s square plus 4 is what is called an irreducible quadratic factor. That means you need to say as plus b over s square plus 4 plus c over s plus 2 and solve this. Dang, I did show you that. Looks like I am a nice guy. So I added the two fractions and the denominators are the same, and so we say the tops must be the same, and s is equal to this blah blah blah, and I gather all the like terms and I make the same argument. Hey, if this were to be, for this to be an identity, the like coefficients must be the same. That is, coefficient of s square on the left hand side should equal the coefficient of s square on the right hand side, and so on. And we get 3 equations and 3 unknowns, and that turns out to be this, ladies and gentlemen. And so Laplace inverse of that is, oh crud, it didn't look like that earlier. Oh man. Okay. So we split that out. S over s square plus 4 cosine 2t. 1 over s square plus 4. We better multiply this by a 2 and divide by a 2 because we want this in the form of k over s square plus k square. K is 2 here. We do not have a 2 there, so we'll artificially introduce a 2, but then compensate for it by dividing by a 2. What? Did you get that? Please pay attention. In order to find Laplace inverse of 1 over s square plus 4, we know if we were to have a k over s square plus k square, then that is the Laplace inverse of that is sine kt. But we don't have a k over s square plus k square. K is 2 here. Since we do not have a 2, the required 2 on the top, let's do one thing. We'll introduce a 2. Let's put a 2 there. But you cannot just introduce a 2. It's a 1. How can you? Yeah, we'll compensate for that by dividing by a 2. Cool. So once we do that, then we have 1/4 sine 2t is what this becomes. And this is 1 over s plus 2 Laplace inverse is e to the negative 2t. That's exactly what I did. Cool. Folks, that's it. So the problems in this section are fairly straightforward. The only thing is you need to know partial fraction decomposition really well. Okay? Okie dokie. And you're responsible for 1 through 34. Thank you.